Rubber processing begins after tapping, when latex is collected in cups and coagulates naturally into cup lumps. Coagulants like formic acid help improve rubber quality, while harmful substances such as sulfuric acid or fertilizers should be avoided. Latex can be processed into cup lumps, slab lumps, thick slabs, or thin sheets. Thin sheets are milled from thick slabs and, when smoked, become smoke sheets. Cleanliness during processing is essential to avoid contaminants like soil, plastic, or used rubber, which lower quality. For storage, rubber should be kept dry, away from sunlight, and on shelves to allow drainage. Grouping cup lumps by collection date is important, as older rubber usually has a higher dry rubber content. To calculate dry content, a sample is weighed, milled, dried, and reweighed. The dry rubber percentage is multiplied by the market price to determine its value. Ultimately, rubber thickness, cleanliness, and proper processing directly influence its market grade and selling price. The automated rubber tapping robot accurately identifies the tapping panel and positions itself against the tree. Using sensors and a precision blade, it performs a controlled cut on the bark without damaging the cambium. The depth, angle, and length of the cut are precisely adjusted to optimize latex flow. After tapping, the robot moves to the next tree, ensuring uniformity and efficiency. This robotic method enhances productivity, reduces labor intensity, and helps maintain tree health over multiple tapping cycles. Styron Deutschland GmbH produces innovative synthetic rubber at Schkopau, focusing on tire performance, sustainability, and quality. Pulse GX50 is a high-performance engineering plastic designed for automotive interiors. Produced using advanced compounding technology, it offers excellent impact strength, heat resistance, and easy flow for complex molding. The process involves precise formulation, testing, and global collaboration to meet lightweight, cost-effective, and sustainable industry demands. The rubber processing process begins with the delivery of raw natural rubber, usually in the form of lumps or latex on site, to the plant. Upon arrival, the material is unloaded onto a receiving floor. Workers manually remove large foreign objects, such as rocks, twigs, or plastic, to avoid damage to equipment and contamination. Next, the rubber is transferred via conveyor to an initial sorting station, where further inspection is performed. At this stage, the rubber is often sticky and uneven in size. Workers use hand tools to break the large lumps into smaller ones. This makes it easier to feed into downstream machinery. After manual sorting, the lumps are transferred to a mechanical feeder, which regulates the amount of material entering the crusher. A crusher is a large machine equipped with rotating blades or rollers designed to cut, grind, or shred rubber into smaller, more efficient pieces. The size reduction process is important to improve the efficiency of the subsequent washing and pressing stages. The shredded rubber is then fed into a washing line. Typically, this process involves long water-filled troughs or rotating drum washers. Inside these drums, the rubber is turned and agitated by mechanical paddles or blades inside. This movement helps loosen and remove adherent impurities, such as soil, sand, and bark. In some systems, the washing line consists of a series of cascading tanks, each stage cleaning the rubber more thoroughly. Water jets may be used to spray the rubber pieces as they move along a conveyor system or drum. Additional rollers or presses inside the washer help to squeeze water and dirt out of the material. The washing process is closely monitored to ensure that the rubber meets cleanliness standards. The dirty water is filtered and recycled or treated before discharge. At the end of this stage, the rubber pieces are noticeably cleaner, smaller in size, and ready for further processing such as creasing, drying, or pressing. This careful preparation is essential to maintain the quality of the final rubber product. The production of rubber using the modern SVR tin line begins with the reception of raw field latex and coagulated rubber. The material is first fed into a shredder to break it into smaller pieces. It then passes through a series of washers and metal detectors to remove impurities and ferrous contaminants. Next, the cleaned rubber is conveyed to a hammer mill for further size reduction and uniformity. After milling, the rubber is transferred into a creping system, where multiple rollers compress and flatten it. The creped rubber is then processed through a cutter to form small, uniform chunks. These are conveyed to a pre-drying stage where excess moisture is removed. The semi-dry rubber is then passed through a hot air dryer to reach the desired moisture content. Following drying, the rubber is cooled and sent through a metal detector once more before being pressed into blocks and wrapped in plastic film. Finally, the blocks are labeled and packed into crates for storage or shipping. The process begins by weighing the required rubber compound components. First, natural rubber sheets are added to the 2-roll mixing mill. As the rolls rotate, the rubber softens and is gradually broken down. Carbon black is slowly introduced to the rubber sheet to improve its strength and durability. The operator continuously folds and stretches the mixture on the mill to ensure even distribution. Next, processing oil is added to enhance flexibility and ease of mixing. Zinc oxide and stearic acid are incorporated to activate the vulcanization process. Then, accelerators and antioxidants are mixed in to improve curing time and resistance to degradation. Finally, sulfur is added to initiate vulcanization. Throughout the process, the compound is repeatedly cut and fed back into the rolls to ensure homogeneity. Once mixing is complete, the rubber sheet is removed, folded, and left to rest before the next production stage. Rubber is manually fed into the roller mill, where it passes through 2 large rotating rollers. These rollers press and flatten the rubber as it moves through the adjustable gap between them. The gap can be precisely set to control the thickness of the rubber sheet as the rollers rotate. The rubber continuously cycles through the rollers multiple times to ensure uniform thickness and consistent quality. The rollers are driven by an electric motor through a gearbox system. The speed of rotation is adjustable using a control panel, allowing operators to fine-tune the rolling process. Throughout the operation, the rollers maintain a synchronized motion to provide steady pressure and consistent output. The process continues until the rubber reaches the desired form and thickness. The PE and EVA sheet separator operates with a user-friendly PLC interface and a computer touchscreen, making it easy to operate. The operator loads the rubber sheet onto the conveyor, and the machine begins the automatic separation process. The blade position and thickness settings are all precisely controlled and repositioned by the PLC system. The sheet is fed through a rotating blade, which cuts it into thinner layers, achieving a tight tolerance of plus or minus 0.05 millimeters. The machine is capable of separating sheets as thin as 0.2 millimeters. During operation, the system automatically counts each cut piece. Additionally, a dust collector is attached to the blade grinder to maintain cleanliness. The touchscreen interface displays real-time operating data, allowing for easy adjustments if required. After separation, the processed sheets exit the machine with a uniform thickness, ready for further use or packaging. The process is efficient, accurate, and requires minimal manual intervention. The HDPE pipe is securely clamped into position. The operator selects the required cutting angle on the control panel, with the machine supporting angles from 0 degrees to 67.5 degrees. The computerized system precisely adjusts the saw blade position. Once set, the bandsaw automatically feeds at an adjustable speed and begins cutting through the pipe. The blade moves smoothly across the pipe surface, ensuring an accurate and clean cut. Throughout the process, the machine monitors blade condition and automatically stops if a break is detected. This ensures safe, efficient operation. After cutting, the finished pipe section is ready for welding into elbows, T's, or crosses. The process begins with an operator carefully placing a large stack of EVA foam rubber sheets onto the feeding platform of the machine. The sheets are aligned properly to ensure accurate processing. Using a guiding system and side rollers, the machine adjusts the position of the sheets to maintain a straight feed path. The feeding system operates automatically and slowly advances the sheets toward the cutting section. As the material enters the processing zone, a vacuum suction bed activates beneath the foam sheet. This vacuum system plays a crucial role throughout the operation. It securely holds the sheet in place, preventing any movement during the cutting and slitting process. This ensures maximum cutting precision and consistent product quality. The first operation performed by the machine is horizontal sheet splitting. A sharp horizontal cutting blade moves downward and begins slicing through the thickness of the foam sheet. The cutting depth is precisely controlled by the machine's internal system, ensuring that the sheet is evenly split into two thinner layers. The vacuum holds the sheet firmly during this stage to avoid lifting or shifting, which could cause uneven cuts or material waste. As the cutting blade advances through the foam, it completes a full-length cut along the horizontal axis, dividing the original sheet into upper and lower layers. After the cut, both layers continue moving forward on their respective conveyor belts. The upper layer is gently lifted and redirected onto a secondary conveyor path, while the lower layer remains on the main conveyor line. The vacuum system continues to operate beneath both layers, ensuring they remain flat and fixed throughout the movement. Next, the machine performs the longitudinal slitting operation. Rotary slitting blades, which are circular and razor-sharp, are lowered into position above the foam sheet. These blades are mounted on adjustable arms, allowing the operator to customize the number and spacing of slits based on the desired product specifications. As the foam sheet moves forward, the rotating blades cut vertically along the entire length of the sheet, dividing it into multiple evenly sized strips. During slitting, the vacuum system once again stabilizes the sheet to ensure that the vertical cuts are straight, accurate, and uniform. The rotary blades spin rapidly, slicing cleanly through the material without tearing or distorting the foam. The result is multiple narrow foam strips with consistent dimensions and smooth edges. After cutting, the individual foam strips are transferred to the machine's feed section. The cut pieces are automatically sorted and stacked in order. Stackers collect the strips into piles, ready for packaging or further processing. This automation eliminates the need for manual collection, reducing labor intensity and improving efficiency. Thicker sheets can be processed multiple times if needed. The operator can reload previously cut layers and repeat the separation or cutting steps as needed. The machine offers flexibility in handling different sheet thicknesses and sizes, all controlled through an intuitive digital interface. Throughout the entire process, the vacuum function plays a key role in maintaining accuracy, safety, and speed. It enhances material control during cutting, minimizes waste, and ensures high output quality. The combined functions of automatic feeding, vacuum holding, cross-cutting, rotary cutting, and automatic stacking make this machine the ideal solution for high-volume EVA foam processing. The installation process of a heavy-duty industrial tire, such as the 19.5 L24 excavator tire, requires a precise, methodical approach that emphasizes safety, lubrication, and mechanical control. The procedure begins with careful preparation of the steel rim and tire to ensure a smooth and damage-free mounting. First, the technician applies a generous amount of specialized rim lubricant to key areas of the rim using a wide paintbrush. The lubricant is spread evenly along the outer circumference of the rim, including the drop center, flange, and bead seat areas. This lubrication process is essential to reduce mounting friction and minimize mechanical stress on the rubber during installation. By allowing the tire beads to glide smoothly over the sharp edges and curves of the rim, the risk of bead tearing, pinching, or misalignment is significantly reduced. In parallel, the outer edges of the rubber tire, specifically the inner and outer surfaces of both beads, are thoroughly coated with lubricant. This ensures compatibility between rubber and metal and helps maintain the tire's structural integrity throughout the installation process. The use of bead lubricant also facilitates uniform bead placement and assists in achieving a secure and airtight seal once the tire is fully mounted. With both the rim and the tire fully lubricated, the rim is positioned horizontally on a stable working surface. Laying the rim flat allows for optimal control and leverage during the manual installation process. Due to the tire's size and weight, proper body mechanics and tool use are essential to ensure efficiency and prevent injury. The technician carefully aligns the tire so that the first bead rests above the rim edge. Using a heavy-duty tire iron, the operator begins to work the first bead into the rim's drop center. This is achieved by applying steady downward force in a circular motion, either clockwise or counterclockwise, depending on the technician's preferred working direction. The bead is gradually pushed over the rim edge using the tire iron, while the technician simultaneously uses body weight to aid in the downward force. This method allows the bead to stretch just enough to slide over the rim without causing permanent deformation or structural damage. Once the first bead is fully seated in the drop center, the technician prepares for the installation of the second bead. Before proceeding, the top edge of the rim and the second bead receive a second coating of lubricant. This additional layer ensures continued lubrication and provides an extra margin of protection against potential bead pinching, especially since the second bead requires more force to install. The second bead is installed by starting at one section of the rim and gradually working around its circumference. The technician uses 2 tire irons or pry bars to leverage the bead over the rim in small increments. The process involves holding one section of the bead in place while prying the adjacent section forward, creating a progressive jumping motion. This step-by-step method distributes the mounting force evenly, helping prevent overstretching or cracking of the bead.
Súbete, ¿no? Es más fácil. Súbete. Sácala, Story.
To further support the tire during installation, the operator may rotate or slightly tilt the rim to gain better tool access and more ergonomic working angles. These small adjustments improve efficiency and reduce strain on both the technician and the tire. In cases involving particularly large or stiff tires, a second technician joins the process. Together, they stand on the rim for better control and use long pry bars to gradually maneuver the second bead over the rim edge. This cooperative effort ensures the tire is seated snugly without misalignment or mechanical stress. Throughout the entire procedure, close attention is paid to tool placement and applied force. Misuse of tools or improper leverage can lead to serious damage such as rolled beads, punctured casings, or scratched rims. Proper technique demands patience and a well-developed sense of tactile feedback, enabling the technician to feel resistance changes and make micro-adjustments in real time.
Ahí está ya.
Lubrication continues to play a vital role during the final bead seating phase. As the last section of the second bead is maneuvered into place, the operator carefully monitors the alignment and seating depth. If necessary, minor readjustments are made by repositioning the tire or rotating the rim slightly to achieve optimal tool contact and avoid uneven mounting.
Al revés, ¿no? Con la curvita. Con la curvita. La que tiene curva.
Upon completion, the technician visually inspects the entire bead area to ensure both beads are seated evenly around the rim. The goal is to confirm full engagement with the bead seat and to identify any signs of bead twist, warping, or extrusion. A well-mounted tire should sit flush against the rim without gaps or irregularities. Proper lubrication ensures that the mounting process did not compromise the rubber's elasticity or cause unintended damage. In conclusion, mounting a large industrial tire by hand involves a systematic series of steps guided by technical skill, physical strength, and attention to detail. From surface preparation and lubrication to bead alignment and seating, every stage is critical to achieving a secure and airtight tire installation. When executed correctly, this process not only extends the service life of the tire, but also ensures reliable performance under the demanding conditions typical of construction and heavy equipment applications. The robotic tire and wheel assembly system begins by using a 3D vision-guided robot to identify the wheel and tire positions. The robot's gripper securely holds the wheel, and another arm aligns the tire. Lubricant is applied to the rim surface to ease installation. The robotic arm then presses the tire onto the rim with controlled force, ensuring precise mounting. The system adjusts automatically for different sizes and positions. Throughout the process, sensors verify alignment and placement accuracy. The robot's movements are smooth, fast, and highly accurate, reducing manual labor while increasing efficiency and consistency in tire installation. The tire assembly process begins as the wheel moves through the motor-driven indexing conveyor to the wheel vision station. It is then soaped at the wheel soaper station. Meanwhile, tires accumulate and are singulated at the tire vision station. After authentication, each tire is soaped and rotated to align with the wheel's low point. Once match-marked, the tire is mounted onto the wheel. The assembly is then inflated, flipped if needed, and transferred to the balancing system. The tire changing process begins by rolling the wheel into the carriage without lifting. The operator powers up the machine, positions the wheel, and clamps it securely. The wheel is then raised to working height. Using the bead roller, the inner and outer beads are loosened. The tire is pushed off the rim. For mounting, bead pliers are installed, and tire and wheel indexes are aligned. After applying lubricant, the tire is pressed into the carriage and rotated. Mounting is completed using the hook method. The alloy wheels are sandblasted, then given 3 coats of powder coating and a diamond cut finish. A clear ceramic layer is applied. Next, the tire is mounted on the wheel and the wheel is mounted on the vehicle. The cutting process begins with positioning a Goodyear 700 by 15 6-ply tire for halving.
Oh, that's so nice. And then we begin.
First, the operator uses a dual saw to penetrate the outer tire surface.
Performance anxiety here.
Once access is achieved, the stainless steel tungsten carbide tire cutter manufactured by General Electric is used. This tool features ergonomic handles and parallel rotating blades designed to slice through thick rubber. The blades are inserted into the central rib of the tire, a design element that conveniently guides the cut. As the cutter moves forward, it cleanly splits the tire along its center line. Occasionally, the operator adjusts tool positioning and blade alignment to ensure smooth penetration. The machine's high-performance blades enable consistent cutting force. After several steady passes, the tire is completely halved. The process highlights both the durability of the cutter and the precision of its tungsten carbide blades, resulting in a clean, even division of the tire into 2 parts. The cutting process begins by placing the used tire on a flat surface. First, the operator uses a cutter to cut back and forth through the inner ring of the tire, following the circular groove around the rim. Once the inner side is completely cut, the tire is turned over and the process is repeated on the opposite side. Once both inner rings are removed, the tire becomes more flexible and easier to handle. Next, the operator proceeds to cut the tire into smaller pieces. Using the same cutter to cut, the tire is cut lengthwise and crosswise into several pieces. A solution is added to each cut to make the cutting process easier. The cutting process is done carefully, with both hands controlling the cutting tool. The mechanic securely mounts the tire onto a specialized tire repair stand equipped with a built-in heating element at the base. This integrated furnace softens the rubber, facilitating easier disassembly. Using a heavy-duty iron pry bar, the mechanic first attaches the steel retaining rings that hold the tire assembly in place. He then inserts the tool between the bead and rim to pry off the outer tire layer. Once separated, the wheel is laid flat on the ground, and the inner tire section is carefully removed for further inspection or repair. This methodical process ensures minimal damage to the components and enhances efficiency. The same steps are systematically repeated for the remaining wheels, maintaining consistency in the repair workflow. This technique is commonly used for repairing large or industrial tires that require heating for successful disassembly. The truck tire refinishing process begins with the old truck wheel being positioned in the refinishing machine. The old tire tread is first polished to remove worn rubber and prepare the surface. Next, a layer of rubber cushion is applied evenly over the polished area by the technician to ensure proper bonding. A new tread is then carefully fabricated and aligned to the tire. Once the tread is in place, the tire is wrapped in a flexible rubber sleeve that serves to seal and protect the tire during the vulcanization process. After wrapping, the tire is mounted on a special vulcanization rim to maintain its shape and pressure. Finally, the prepared tire is placed in the vulcanization chamber, where heat and pressure cure the materials, bonding the new tread to the old casing and restoring the structural integrity of the tire. This process ensures that the refinished tire is durable and suitable for continued use on trucks. To regroove a tire, the technician begins by assessing the tire to ensure it can be regrooved. Using a heated regrooving tool, he carefully cuts new straight grooves that match the original tread pattern. As the blade cuts into the rubber, it removes a thin layer, deepening the grooves by about 2 to 3 millimeters without touching the steel belt. The tool simultaneously heats and cuts through the tread, ensuring a clean cut. Next, he cuts small horizontal grooves across the tire's surface. The operator works systematically through all sections of the tread, maintaining consistent depth and spacing. Safety precautions are followed throughout the process, and only marked tires are selected. This controlled cutting restores the tread pattern, improving traction and extending the tire's service life without compromising structural integrity.